Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. So today's session we're going to talk about the last part of week number 3 that we need to learn. So it is about introduction to divergence concept and divergence theorem. So that should be the topic of discussion in this particular session. Introduction to divergent concept and divergence theorem. So I'm going to talk about divergence concept here. Okay, so divergence. I presume most of you have heard about this issue in engineering mathematics. So for those who have or haven't heard about this issue, I would suggest you to read yourself from our textbook. If you refer to page 177, okay, section 3.5, you can see some explanation given by Sadiku about the concept of divergence, which I'm not going to discuss in this particular discussion. What I'm going to do here, I'm going to talk about the application of divergence in the world of electrostatic domain. Okay, with that, what I'm going to do, I'm going to extend the title of discussion to become divergence of the current field that we are dealing now, D. So what D representing? Electric field density. That should be what we're going to talk about in this particular session. The application of model divergence with regards to electrostatic field. So let's assume, let's say you have a space, and the space that we consider filled with electric field. So let's presume that we have electric field. And then the electric field that we have here, we specifically define it to be D. And D, we know, representing electric field density. So what we want to do here, we're going to do some sort of model analysis or mathematical model analysis at the point dot here. So what model of mathematical model that we want to use in this particular analysis is known as divergence model. Okay, so what we're going to talk now, the application of divergence model, such that we want to understand what happened to the field D when we use the model divergence in this analysis. So that intention can be presented in mathematical equation given as this symbol. Divergence of D is seen to be presented by this mathematical equation. So whenever you see this symbol, that representing the model known as divergence model. If the field here D, divergence of D. If the symbol here given as F, so divergence of F. From the term del here, we can see this model is coordinate dependence. So meaning that because we have the notation del notation in this equation, therefore we can assume, we can deduce that this term is coordinate dependence. And we know that in terms of EMT, there are 3 different coordinate systems that we can define, which are the first one, we call it to be Cartesian. Okay, the second coordinate system that we have learned before is cylindrical. And the final coordinate system that we use known as spherical. So this model, when you categorize under Cartesian, there are a set of equations that you can refer, and that's given by our textbook. So Cartesian is defined by the equation 3.29. So when you refer to equation 3.29, that is the equation representing divergence model based on which coordinate? Cartesian. If I'm referring to equation 3.30, that will be the divergence model based on cylindrical. And finally, when I refer to equation 3.31, that's going to be the set equation of divergence model based on spherical. And all these three equations actually you can refer from our textbook on the page 79. Okay, I'm not going to write the equation, it's quite lengthy. So what you can do, you can refer to the textbook about this equation. Okay, so that should be the idea that we're going to deal with regarding divergence model in our electrostatic world. What is it? Let's say we have the field given in space. We want to analyze that field based on the divergence model. So that particular task need to be implemented by referring to the set equation based on various coordinate system. Okay, that's the idea of divergence that we need to know for our EMT subject. We're not going to define it, or we're not going to derive it, because that should be done already in your engineering mathematics subject. But at this stage, we're going to use it. So let's recall, let's do one example, a typical example that we can use this idea. So I'm going to talk about example now. Okay, I think if we recall the problem we did from handout number 5, then question number 3. I think you can still recall that particular problem, the first Gauss law example we did together, where what we've been given a sphere, and then that sphere contain charge volume. Okay, and then we given that symbol as rho v, and then we also know the radius of our sphere is given as a. And then from our exercise, we managed to obtain two distinct fields. Okay, one field is referred to region inside the sphere. Another set of field we obtain for region outside the sphere. Okay, so what we obtain for inside the sphere, okay, so the D1, if you refer to your solution, is equal to what? Rho v r over 3 in r direction. That's the solution that we obtain. And for region outside the sphere, D2 is equal to rho v a cube divided by 3r square in r directions. Okay, that is the result we obtain using Gauss law based on this structure that's shown here. So what we're going to do in our example or in our discussion now, what should be the solution of the divergence of D1? Okay, that's what we want to solve here. What should be the solution for this particular model mathematics for divergence of D1, and what should be the solution of divergence D2. Okay, that's what our objective in this particular discussion. What should be the solution for this field using the divergence model that we studying now. Okay, to answer your problem, what we can see, the first thing that we must deduce is to define which coordinate system that we use to solve this problem. And I'm sure most of you can recall the coordinate system that we adopt for this particular problem solving last time is spherical. Okay, so therefore the logical step here, when we want to solve divergence model, we must refer to the set equation, and we are focusing on spherical, therefore we must refer to equation 3.31 on page 79. Okay, let's do that now. So what I obtain from that equation as shown to you now is quite lengthy. Okay, so this is what we have to refer. So focus especially for spherical coordinate. Why? Because we are using spherical coordinate as our adopted coordinate system previously. So therefore we must use this to define the divergence model for the field. So the first one that we want to do is divergence of D1. Okay, so what we have to do here, we have to analyze the field. So D1, as you can see in this particular representation, is only consists of R component. Therefore, this actually defined as the magnitude dr. Okay, so we can see from the solution dr only contain the R component of spherical coordinate, and the magnitude of dr is given by rho vr over 3, and we don't have any representation with regard to the theta component as well as the phi component. Okay, so therefore what we have to do, referring to the set equation we are referring, we can see now when I substitute the equation, I have to substitute the magnitude of the d, and then we know that from our d1 is only contain the dr component, which I'm writing now, which is rho v r over 3, and you can see I just substitute the magnitude of the vector d1 in r component. Okay, there's no direction here because here the substitution needed is only the magnitude of the dr. Okay, that's done. Then I'm going to continue with the others part of the equation. Okay, d over d theta, and then as you can see now, the d theta need to be substituted with 0 because d1 does not have any d theta component, and other than that should be as it is. And if you put into the third component here, the r sine theta d over d phi, and also we know for the phi component of d1 also equal to 0. So that's what you need to do. We have to substitute accurately into the set equation the component of field representing our d. So therefore in our example here, the d1 only contain the r component, therefore you can see it's being substituted in this part of the mathematics. Other than that, for the theta component of the D as well as the phi component of the D will be equal to 0. So when you solve the mathematics now, what we can do, we can see here, okay, the term here will become 0. The term here also will become 0. We only end with the first component now. So if I do the mathematics now, what I can see should be 1 over r square. Then I'm going to see, I can take out the rho v. Okay, I can take out 3 as well. And then we're going to have what here? D over dr of r cubed. Because the r square multiplied with the r will give us r cubed. When we solve the mathematics, what we're going to end with should be 3r square. The 3 and this 3 will cancel out. R square, so we're going to end only with the rho v. Okay, so that should be the final solution of our model mathematics of divergence regarding the field in region number 1. Okay, so therefore what we can conclude, the divergence of D1 is equal to rho v. So let's ask ourselves, okay, let's look back into the model. You can see clearly from this particular example, actually in this region is filled with what? Yes, it's filled with volume charge rho v. So after using the divergence model of the field, you can see the end product of that model mathematics is actually the volume charge. Okay, so what we can conclude here from the given field, okay, even though we do not know about the distribution of charge, when we have the field, by using the model divergence, we can detect whether the region where we're going to analyze the field actually contain any source or not. And from this first example, you can see clearly by modeling the divergence model of D1, it will give us it containing a volume charge, and that is true. That's what the model that we did in the this one example we did together, where the region in region 1 is filled with volume charge. Okay, so therefore you can see the divergence model is actually reverse process of Gauss law. In Gauss law, you know the charge, you can determine the field. But with divergence model, knowing the field, we can deduce whether at the certain point where the field is being analyzed, there is charge or no charge. Okay, let's try it with the second field. And we know in the second field, the region here does not contain any charge. So logically, the solution of the divergence of D1 should become 0. So let's prove it. Okay, for region number 2. Okay, region number 2. Okay, divergence of D2. So I'm going to use the same formula, 1 over r square d over dr, and then r square. Then I have to substitute with the r component of d2, that is equal to rho v a cube over 3r square. Okay, that's the substitution. And then we don't have to bother about the theta component and as well as the phi component, because we know similar as above, there's no theta and phi component of D in region number 2. Okay, let's simplify the mathematics. I can cancel this term, r square and r square. Now I differentiate a constant value, and the final solution here is equal to, as expected, 0. Okay, so therefore that's a proof that what we are dealing now, we can say as a conclusion, the divergence of D is equal to rho V. Okay, so that should be our conclusion, and this equation is very important in the world of electromagnetic, and we call this equation as Maxwell equation number 1. Okay, and if you refer to our course learning outcome number 2, it clearly states about Maxwell equation. Actually, we're going to learn about 4 Maxwell equation. The first Maxwell equation is as shown here. So this is what we call it to be Maxwell equation number 1. Okay, so I'm going to summarize what we have learned until now using this simple graphical representation. Okay, what we have learned so far in this subject, in the world of electrostatic, we know that the source of electrostatic is stationary charge. Okay, that should be the source of electrostatic. We know the source can produce electric field intensity, E, and another field that can be produced is electric field density. Okay, before we can determine E from the source using Coulomb's law, and then we can determine the D from the source provided is acceptable because there's a certain condition that we can use Gauss law. Okay, so therefore that should be what we have seen so far. And now in this session, what we have seen from the D, we be able to determine the source, and that is known as Maxwell equation number 1. Okay, so that's what we can conclude until now based on the discussion that we have until now regarding electrostatic domain. Okay, I'm going to end the discussion with another important model mathematics. We call that model as Divergence Theorem. Okay, so that's what we're going to talk now. Divergence Theorem. Okay, so let's recall Gauss law. Okay, I'm going to call it from Gauss law. We know that the equation can be presented as d dot ds equal to q and cross. And then based on this simple graphic presentation, when we are dealing with volume charge, so we know that to find the total charge for a volume charge can be represented by this mathematic rho v dv. Okay, and from our simple calculation we did together just now, that the rho v here actually can be substituted with Maxwell equation number 1, divergence of D. Okay, so when we rewrite the equation as such, so what is it? So when I do the mathematics of the field with respect to surface integration, okay, I can convert it to be in the volume integration when it follow these laws. Okay, so what this equation state, we can convert surface integration to volume integration, or from volume integration to surface integration using this set of equation. And this equation is known as divergence theorem. Okay, so therefore I have explained to you about two main important parameters, and one is known as the divergence model, and the second is known as divergence theorem. So with that, I'm going to end my discussion, and then this issue, or this the thing that we discuss here, going to be used a lot in our next session. So hope you do understand what we are talking now, because again, I'm repeating here, we're going to see a lot in our next discussion. With that, I'd like to thank you for your attention, and inshallah we're going to see each other in our coming session. Assalamu alaikum wa rahmatullahi wa barakatuh. Thank you.